Hi, your first homework video is going to be on describing matter. We're only going to get through slides 1 through 18, and some of the slides in this presentation have practice questions, and you're going to answer them as you go along. We're first going to start this unit describing matter. Let me put this in presentation mode so you can see everything much better. When we talk about matter, we're going to take measurements like mass and volume, and we'll learn as we go along that energy is different. Energy is not made up of matter. You can't measure it and quantify it in terms of its mass and volume. All right, moving on. What we're really going to do is spend some time organizing and categorizing things based on titles. I want you to be able to understand matter as how we define it, how we use particle diagrams to pictorially represent it, and chemical formulas. So those are the big three. If we look over here on the left, the word substance. If you look at these particle diagrams, a substance is pure. That means that every particle pictured to represent the substance is the same kind of particle. Here, for compound, you see, I have to go back. Hold on. How do I go back? All right, let me do this. Oh, that was annoying. Okay. If you look at the circle here, you have one gray circle with two red circles attached to it. The minute the particles are attached to each other, they are chemically combined. So a compound is two or more substances that are chemically combined. This gray circle and the two red circles, once they're all attached, they behave as one thing. They have a new set of properties, they have their own name, and they have a chemical formula that shows them as one substance. So even though there's two or more elements here, and I could break this down into the gray particles and the red particles, it's a compound. So it's a combination of elements chemically bound together. But once they join together, this particle acts as one particle. And this is the same particle with the same properties and the same identity as this particle. So they both fall under the umbrella of being pure substances. If they're mixtures, well, then there are two or more substances that are physically combined, not chemically combined. And if those particles remain separate from each other, like this would be oil and water, if they don't intermingle and uniformly disperse and spread into each other's space, well, then it's a heterogeneous mixture. If it's a homogeneous mixture, then one type of particle mingles and mixes and intersperses into the space with another type of particle, like these orange circles and these double green circles. Now, the double green circles, since they're the same type of circle and they're touching, it implies a chemical bond, but if a green particle and another green particle bind to each other, it's still the same substance. It's still an element. It's just two atoms of the same kind. We call that a diatomic element. So the orange circle is one element. The two green circles, that's another molecule of a different element. It's just an element that's so reactive that it binds to an atom of its own kind. Here, this is a compound and a different compound, and they won't mix together. They maintain separateness, and you can see them as separate and distinct. Now let's look at this. I have up here a block of iron, and on the top right I have chunks of a solid yellow substance that's sulfur. Sulfur is the stuff that makes matches smell the way they do. A lot of people think sulfur is what makes rotten eggs smell or hard-boiled eggs. That's a different compound. Sulfur in and of itself smells like the tip of a match, and this is iron. I can't crush iron into a powder, but I can scrape it into something called iron filings. This is brittle and I can crush it into a powder. And if I took the iron filings solid and the orange powder solid and I mixed them together, I would get this sort of dirty, mustardy, yellow solid mixture. And because iron is magnetic and sulfur is not, I can still separate that mixture physically by putting a magnet in there and pulling out the iron filings based on the fact that iron retained its properties. It's darker in color when I scrape it into filings. It's magnetic and it retains that solid magnetic property that it had. And the sulfur still has its yellow color. It's only dirtied and darkened by the presence of the iron filings, making it not as bright and vibrant. But it's still a yellow solid and it's still not magnetic, and it would still maintain its smell. This over here on the right is pyrite. It's called fool's gold, and it's basically iron sulfide. It's a mineral in which the iron and the sulfur have bonded together, and they don't retain any more of their properties. This is not brittle and bright yellow. It's got metallic luster, but it's not iron anymore. It's got a different color, and it's no longer magnetic. So it's got completely different properties. It's got some properties of the metal in terms of its luster and its shine, but it doesn't have all of the properties that a metal would have. So it's kind of got a new set of properties that does not belong to either one of its component elements. If I wanted to chemically break this down, I could put it through a chemical reaction and I could return it back to iron and sulfur by chemically breaking it down. Now, when we talk about mixtures, this is sugar water, that's sand plus water, and that's salt water. The reason I said sand plus water is because you can see the sand separate from the water. The sand does not dissolve. So the sand stays at the bottom and the water above it. Those two types of matter maintain their separate phase of matter. One is a solid and one is a liquid. When I put solid sugar crystals into the water and I stir it up and it dissolves, now it's an aqueous solution. I would put the formula for sugar, and then I would put in parentheses next to it the symbol AQ, standing for aqueous. And that would tell me that the solid sugar mixed with water and made an aqueous solution. The same thing for salt. NaCl is table salt, sodium chloride. And I would say NaCl, and in parentheses I'd put AQ. And that would tell me that the salt dissolved in water, making a homogeneous solution. Now, when we go back to pure substances, the very definition of an element is that it cannot be broken down chemically into simpler substances. When we look at their formula, they all have at least one capital letter in their formula, and if there is a second letter, it's lowercase. Look at calcium, Ca. If it was just one C, capital C, that's carbon. So since carbon has already been used for the letter C, calcium can't also be C. It has to be Ca. So there's no other element that has A as its second letter except for calcium. Any other elements that start with a C, like copper, we would do Cu. Now, copper is Co. Why wouldn't we do Co? Well, that's cobalt. So Cu comes from the Latin word cupric, and that's where the U comes from. So copper-based compounds are cupric or cuprous compounds. So we'll slowly get to learn the periodic table of elements. But generally speaking, if only one of the letters is capitalized, you know it's an element. But if I had capital C, capital O, well, then you would know, oh, I'm chemically combining carbon and oxygen. That's a compound. So if you look, compounds have two or more capital letters, H2O, NH3. Notice both letters are capitalized, CO2 and H2O2. And if you look at their particle diagrams, the circles are touching, and the color, the shape, and the size, and the symbols used are different. So a compound is two or more substances that have been chemically combined, and their proportions are fixed. Now, the reason that last part matters, look at water and hydrogen peroxide. Do you see how they have the same two elements, hydrogen and oxygen? Well, this one has only one oxygen for every two hydrogen, and this one has two hydrogen for every two oxygen. So completely different properties. If you were to drink this, perfectly safe, perfectly normal. If I were to open up a bottle of hydrogen peroxide and drink that, it would be toxic and lethal. You would never want to drink it, even though it's got the same component elements, vastly different properties. If I poured this over a cut, it would wash the cut out. If I poured this over a cut, it would fizz and start to chemically break down because the enzyme in my blood would activate the decomposition, breaking it down into water and oxygen. Very different properties. More of the same. If you have an ionic compound, we often use their basic ionic formula. We call it a formula unit to write the compound. So this crystal with the green circles being chloride ions, and the purple circles being sodium ions, every time I have one purple, I have one green that goes with it. So every formula unit, it's a 1-to-1. So the formula would be NaCl. I wouldn't use subscripts to indicate how many greens or how many purples I have in a crystal because the size of the crystal, a salt crystal can grow and shrink and its properties don't change. So if I have a small salt crystal with only a couple of sodiums and a couple of chlorides, it will have the exact same properties as an enormous salt crystal with many more ions of each kind. So we simplify it and we call this the empirical formula. We've written down the smallest whole number ratio, which in this case is 1-to-1. For every sodium, there's one chloride. When it comes to molecules like water and carbon dioxide, the subscripts matter, like H2O versus H2O2. In that case, we're not writing the empirical formula. We're writing the exact number of each kind of element found within a single particle called a molecule. All right, so now what I want you to do is I'm going to pause the video here and you're going to answer this question and then you'll answer the next question. So I'm just going to click through them, and when I put this into Edpuzzle, you'll have questions to answer. So now you will read this question and you will answer it. Pause the video. Again, pause the video so you can read it and answer this question and this question. All right, and now we're on to particle diagrams. Particle diagrams are where we use circular symbols to represent different kinds of atoms. They might be small, large, have different color shadings, a different pattern. If it's a black and white diagram, I might make a plus sign inside or diagonal lines, or I might shade it. I might put a dot in the center, just so you know that it's representing a different kind of element. When the circles are touching, then you can tell that they're a compound. When the circles are separate but yet different, then they're just being mixed together. So look here. A hollow circle is element T. A hollow circle with a dot is element X. And a hollow circle with a vertical line is element Z. Which two models can be classified as elements? So this is model 1, 2, 3, and 4. And you might remember that I told you when all of the circles are the same kind of symbol, then it's only an element. So this is 2 of the same symbol. So this is an element, but it's diatomic. Here, all 4 are the same. So this is also an element. But here, the circles that are touching are different kinds. So that's a compound, and the same is true over here. So now that I've answered that one for you, you're going to mark down the answer in the video, and then you're going to go through and pause the video here and answer the question. Pause the video here to answer the question. Pause the video here so you can look at the question to answer it. All right, and then finally, I think we're at the end. Yeah, tomorrow in class, we're going to go over particle diagrams, elements, compounds, and mixtures. Oh, wait, I'm going to continue just a little bit longer. A mixture is defined as 2 or more substances physically combined, but their proportions can vary. I can have a glass of salt water with 1 spoonful, or I could put an entire cup. As long as it all dissolves, whether it's a spoonful or a cup, it's still salt water. The amount of salt to the amount of water is not fixed because there's no chemical formula. If I write AQ, again, that means aqueous. It means it's dissolved in water. If the 2 substances are separated by a plus sign and they maintain their separate phases of matter, liquid and solid, then They are mixed, but they are not homogeneous. They are heterogeneous. All right, you're going to pause the video here. Answer the question. Let me move this so you can see all the choices. I can't find a spot. All right, I think that blocks the least of the question. Answer this question and this one. All right, we're going to get into this stuff tomorrow, so I'm going to stop the video here. Let me hit escape. See what slide I got up to. All right, I'd only wanted to get up to slide 18, but I actually went all the way to slide 23. So we're going to end on slide 20.